Hello community, let's talk about the latest scientific problems we have with GraphRAG scaling. Now, today we go a little bit from PyG2 to an advanced graph neural network reward system based on a GraphRAG system, and our intention is to build a full stack analysis of the latest reasoning system in AI. Now you know standard graph, and then we develop GraphRAG, knowledge here as a graph on entities and relationship. And the core is simply move here the information from a flat list to a knowledge graph, and of course the optimization via a graph neural network. Now a GNN is essentially an advanced GraphRAG system for two reasons, and it is enhanced semantic retrieval and a representation learning for reasoning. And I will show you that a GNN we have now as a reward model. So you might say, okay, so how many elements do we have now in the game? Just show me what we have. Well, it is easy. Now we have GraphRAG, we have the strategy, this is the overall paradigm. Then we have an agentic framework. Then we have the classical transformer. Then we have our graph neural network optimized here for graph entities. And finally, we have the knowledge graph itself. We will work with multiple knowledge graph, a structured representation of the world knowledge, which we assume to be correct, the truth. So I was asked by a lot of my audience, hey, can you give us here an introduction, explain everything what you're going to talk about in this video, but do it for beginner and do it for expert. So I will try this here the very first time. If you don't like it, skip here the next 2 minutes and I will continue in my normal way, but let's do an experiment. Let's see if this is what you are asking for. Let's start with for beginners. That's rather easy. We have retrieval-augmented generation. We have a multi-hop reasoning. We build large-scale knowledge graph. Advanced strategy is the GraphRAG system we talked about in the last videos. But, you know, in the moment we operationalize here the paradigm on real-world knowledge graph, if we go from thousands or hundreds of thousands of elements here to maybe millions of documents, it becomes real expensive, real fast. So, this is now the idea. We have to have a hierarchical cognitive architecture. Each layer provides the necessary abstraction and capabilities, and I will show you here a new stack how to handle this end-to-end in the reasoning pipeline. Now for experts, yes, I know you're waiting for this. Who's an expert? If you have seen all my videos about PyG, 2 years ago, 3 years ago, graph neural network here, all the code about graph link prediction with DGL on PyTorch, and a PyG code example with graph machine learning and graph neural network. If you have seen everything, you know everything, you work with this, you are an expert. So what we're going to look at, we look at a foundation layer in the PyG 2.0 framework here. And especially we have here the critical I/O and the memory bottlenecks that we're going to attack. Because we will use now two keys, the graph store and the feature store abstraction. This instantiate here a virtualized out-of-core processing model enable our GNN to operate here on subgraphs, finally, sampled from massive non-resident knowledge graph via a programmatic interface. And second, you know PyG2 supports heterogeneous graph powered here by PyTorch and metaprogramming. So it automates now the construction of models with a relationship-specific transformation matrix, which will be a prerequisite for any semantically aware reasoning over diverse knowledge graphs. So we have this new execution layer underpins here the graph neural networks, which function here as a specialized structural encoder. You know this encoder-decoder structure. And I'm going to show you a simple example here of a specific reward model here. That will be a graph regression graph neural network that computes here a very relevant score for a given evidence subgraph, so a higher complexity. And by executing here multiple rounds of heterogeneous message passing within the graph neural network and its subnetwork, it produces here contextualized node embeddings that we gonna then embed. We have a subsequently pulled into holistic graph representation, thereby learning now a structure-aware scoring function. And we will see that this is vastly superior to a simple feature similarity metric. You see, as you ask, everything here on one screen. Now let's continue here with the normal way I would try to explain this and try to learn this myself. Knowledge graph. Now, you know, a knowledge graph, to build a knowledge graph is done offline. Yeah? Knowledge graph construction, you can do this here for some 100,000 elements. Great. You have an offline, so this approach is required. You read every single book in a library ahead of time. You build a knowledge graph, and then you have established here a reference knowledge graph exactly in your domain with the complexity and with the depth of multi-hop reasoning that you require for your particular task. We're going to look at 3 new AI research papers. The first one is GEARS. GEARS is an interesting application of a just-in-time knowledge alignment here to a huge public reference knowledge graph. And here we have the publication. Notice that this is from Huawei Technologies here. So, of course, this is more or less their proprietary methodology. They show us here July 23, 2025. If you're not familiar, I would recommend this paper here, where they introduce you to GEAR. This is June 22, 2025, same Huawei technology, and GEAR is simply a graph-enhanced agent for retrieval-augmented generation. Yeah, we are back, baby, with RAG, GraphRAG, all the way back to RAG in the most complex version you can ever imagine. But let's start here at a flow process chart here, and I think this is the easiest way to explain here the new system architecture. So let's start this. I'm going to help you a little bit. So what we say is we have here our original query queue. This is the natural language question here that I ask you the system. Yeah? Then we simply have a base retriever. Query goes to a standard non-graph retriever. And its job is simply to perform a first pass search over the entire document corpus that I have if I work, for example, in a particular domain like theoretical physics. And then extract my passages. This is the retriever returns here a set of relevant text passages. This is the result of the search if you want. And then we feed it now to a reader. Now the reader, along with the query queue, the passages and the query are fed into the reader module. I'm going to show you here the prompt for the reader module in some minute time. What is? It's another efficient little LLM. They go here, I think, with a 10 billion LLM. And the job is easy. The only job of the reader is to read the text and perform here a triple extraction, a proximal triple extraction, because we only work here on kind of a subdomain subgraph structure, and we have not yet explored the complete complexity that we will need in order to find an answer. So what we have now is something they call T- proximal triplets. So this is the output of the reader of an LLM, couldn't be easier. A small set of temporary informal triplets, you know this structure, subject, predicate, object, extracted direct here from the text passages here of my small domain-specific corpus. That's it. First part, done. Now we come to 2 elements, this they call triple link and graph expansion, that are rather interesting. So yeah, we are here in this SyncGE part, is where the system bridges here the gap between the text world and the graph world, and our triple link is now interesting. So we have both. No? We have the proximal triplets, and this arrow here, if you want, represents here the online knowledge synchronization step. So this is now interesting. So what you need now a link to the monster, huge planetary size database that has the real knowledge of everything. Let's call it Wikipedia or Wikidata. This online knowledge synchronization is the main trick if you want. So each proximal triple T dash here is used here as a search query to find now the most similar canonical triple T, the original triple T, in the massive external knowledge graph of Wikidata. T triples is here the result of the triple link. This is a set of canonical triples from the Wikidata that are now linked to our query. So what we found the entry points into the global graph. And then comes now the interesting element of the graph expansion. It is rather easy if you got here the main idea of this. So starting now from the canonical triples T, the system performs a search within the Wikipedia or Wikidata graph to find new multi-hop reasoning paths. You know this. We talked about this already in my last videos. And you can have different search algorithm, and here in the paper they go with a classical diverse triple beam search algorithm. So this means you don't find just one path on the hypersurface of your knowledge graph, but you explore in parallel multiple promising paths simultaneously to gather here a wider range of evidence. Great, this is it. So what you do have now, additional information. So the new triplets now discovered now during the graph expansion are simply guess what? Use to requery the original document corpus C. So this is the crucial step, The system understood that it learned now additional domain-specific information, and the system uses what it learned from exploring here the graph, the Wikidata graph, to find now new documents that the initial base retrieval might have missed. So we are operating here in a beautiful loop. Now comes the next simple step. This is a reciprocal rank fusion process. What we have now evidence, if you want, from the simple text search that we started with and the advanced graph-based search here. And guess what? We have now two sets of retrieved passages and we fused them together into a single, more robust ranked list. So you see, RF is a simple but effective technique for combining results from different search systems and different search complexity that are close by. And now comes here the agentic part, if you want. Yeah? What we do now is, well, of course, we have memory. We have agent. We don't have pure LLMs. So we have now here, from our passages, we just put it in the memory. And our triplets, we also put it in the memory. And guess what? We will continue to work with those. So here, those boxes here represent here the agent internal state, or if you want, just a scratchpad. If memory is too complex, then it's a scratchpad where the agent now writes here additional information. And after each iteration, the retrieved passages and the discovered triplets are simply stored here. Now we have a simple if-then. If we reach now here to the stop command, and after a full cycle of retrieval and fusion, the agent's LLM, the brain, makes now a decision. Either it says, hey, I found the solution. I think the evidence I accumulated here in the query history is the question now answerable. If it's a yes, it will stop the process. If no, guess what? We feed it back into the loop. And we update here the query, and you see, now we go back, and we start all over again. And now we have additional information that we feed into this process. Yeah, this is simply the rewrite step. I think it's rather simple to understand. So this turns out now to turn the one-shot retrieval process into an iterative, agentic, we're working with memory structures, a reasoning loop that can now tackle more complex problems step by step, because guess what? If we have and the updated query is fed back to the base retriever, we have to make sure that if the complexity, for example, is too high, that now on the way back to the input, we say, hey, wait a minute, I have another LLM and I now reduce the complexity of this specific query. So I divide now the query, let's say a complexity level 7, in 3 subqueries, each has only a complexity level of 3 to 5, and then run again through the process, and then I should be able to maybe find a solution immediately. Of course, you have to have filters, and guess what? Final filter step, so another LLM prompt is used here to prune any irrelevant information here from our golden dataset. And finally, we have an answer generation. Great. And we have either a single step output, if we said immediately we found a solution, or a multi-step output after the agentic loop has completed here for multiple iterations. So you see, it looked rather simple, but you have to understand here what is happening behind those little boxes. And this is where really the fun starts. And you see the complexity is not that complex. We are still building here as human rather simple flow structures. So step-by-step flow shows here a sophisticated system, starts with a simple query, dynamically bridges the gap to a massive structured knowledge base. This is Wikidata that we use. Explore that particular base to enrich its understanding, get all the context information, the context engineering, we would say in today's speech, and iteratively refine here its search until it has gathered enough high-quality evidence to provide here a confident answer to the human. And you might say, but there's a possibility that something goes wrong. Absolutely. We have to talk about this. But in general, let's come back and say, what is more feasible? No? Because what are they trying to tackle here? They say, what is more feasible? Building here a perfect custom knowledge graph from 1 billion documents? Maybe 1 million would be a first good step, no? From scratch. This is really expensive. Okay, Google can do this and Microsoft can do this, but normal user is not going to invest $100,000, $1 million to build the perfect custom knowledge graph for your domain. Or the other way is, hey, let's leverage here an existing, a public available knowledge graph like Wikidata and deal with the noisy process of linking to it. This is now becoming the main topic because B is exactly what we're going to look at and what the consortium Huawei decided to examine here for their AI research. Now I told you here for the gear prompts, here we have the reader and you see example. Yeah, you have exactly your triplet, no? University of Southampton, founded in 1862. So you see a simple prompt. And yeah, you have advanced question answering here with the knowledge triple. So you just have here an autoregressive system, which is not ideal, but guess what? This is all that we have. So I just want to show you here why, in my idea, we do this. No? So we have here the real thing, no? The construction of a real complex knowledge graph. If you're a rich company, you can afford this, no problem. But the costs are simply astronomical if you go into the millions and billions of documents and you build really complex, proven, logical knowledge graphs. No? A massive upfront capital expenditure that could run into, a lot amount of dollars. I don't think anybody would go with billions of documents, but you get the idea. Plus, it is extremely slow. Plus, you must pay and maintain here a potential massive custom graph database. So, my goodness, no? So the idea of gears is simple, no? Let's do not do this. We have somewhere on Wikipedia, Wikidata, somewhere, we have some global knowledge graph with some global domain knowledge. Let's use this for our specific domain task and do it just in time alignment. Now, the advantages are great, no? Minimal operational computational cost. A small efficient LLM, maybe 3 or 4, is used to process only a handful of documents per the query. The cost shifts from a massive upfront here to something, fraction of a cent is maybe a little bit too optimistic, but you get the idea, no? The developing and processing is instantaneous, no? You just need a more or less a internet connection, no? The system here, Wikidata or Wikipedia or whatever you have, is always live and can immediately incorporate new documents. You can add this to a search index. Everything that you build here is real fast. Yeah? So, and what the main idea is here, you leverage 2 pre-existing independently maintained systems. You have a standard text search index that you have on your mainframe, and you have a huge public knowledge graph somewhere in the cloud like Wikidata. No? So, I understand the idea, but as I told you, we do have a problem. Eh? We do have the problem here, and this is how do we solve the misalignment problem. Because remember, we're working with multiple LLMs, and yes, hallucination and everything, but we also have another one. And this is here the errors that might happen here at the API boundary, where it tries to connect its internal findings now to the external resource to Wikidata. And there are a lot of examples now in this publication that show us this is the most critical and error-prone interface where errors might happen. They give you an example and they say, if you try to compare your triplets, no? If you do it on a semantic autoregressive way, you are just looking at the very next token, not at the next word, the very next token. And depending on your tokenization structure, this can be really, really tiny, and it does not understand the complex semantic information that is stored in the triplet. And here you have currently quite a lot or a high potential of mistakes. If you want here the singular view, try to summarize this here if you just want to see this here in one glance here at the screen. Yeah? This is what we just talked about. And then there's the second paper, the main paper here of this video. And I love it if scientists give it here a real beautiful name like QMQ5. So I call it Susan. And what does this stand for? So Susan stands for Query Aware Multipath Knowledge Graph Fusion Approach for Enhancing RAG, Retrieval-Augmented Generation. And you might ask yourself, what is RAG never dying? And you might say, hey, is RAG still here? Is this possible? Yeah, but this is not your classical RAG. This is RAG here in dimension you cannot even imagine. We do now here a knowledge graph fusion in a very multi-path way where we have the standard attention and we have a cross attention and we have a specific GNN reward system that we develop for a Krumpfumke, or as I call it, Susan. So here now we assume option A. We assume you have paid the price to build a perfect self-contained, your domain-specific knowledge graph with your corporate data, with your personal data from your own documents. You went through the process and built here a beautiful knowledge graph. So let's start from there. Because now the challenge is not to find the data, but how to intelligently fuse here the different reasoning paths. And we will work on multiple reasoning paths on the multiple hyperplanes of the knowledge graph, that we have to combine them so we find the perfect answer that exists now in this perfect world. The master plan is simple. Now, it's kind of a strategy. The devices now here plan not to find one path, but evaluate all possible paths simultaneously, given here the knowledge, the parametric knowledge here of our objects. We do have a multipath construction, and I will show you in 2 minutes time. We have 3 elements. We have an immediate surrounding, a one-hop structure. We have a multi-hop structure, and we use here the very old Google PageRank algorithm for the topographical analysis to identify structurally important locations. Then we will use a sophisticated cross-attention model simply to see which scout path is most aligned with the true objectives, and thereby evaluating evidence here in the context of our defined goal. If you're interested in a cliffhanger, yes, there is something we're gonna talk about in the next video. So here we have it. This is here from University of Science and Technology, Beijing, China. And hello Europe! In Sweden, Karlskrona, the Institute of Technology. So nice to see it here, July 7, 2025. And they give us here their beautiful QM or Susan. I have here, if you want to see here, a short summary. You can copy it if you want. And now we'll start here with a detailed explanation in my way. So this is here, if you want a flowchart, this is it. This is the complete framework here of Susan. And you say, okay, this looks quite interesting. And I told you, yes, now we are going to build here constructs that include everything that we know. Because we are now really desperate in AI research because it's not working. So what we do, we combine elements that worked here singularly, and we hope if we combine it here in an intelligent way, that suddenly we will have a better performance. And yes, I will show you the performance data at the end of this video. So we start here, you're not gonna believe it, with the input. So there, and I just go here with the model. So if you want to read in parallel here the paper, you can do this. They have here the first step, entity mapping. What is the goal of entity mapping here? Easy. To find the correct entry point into the knowledge graph based here on the particular user query, on my human query. So we have here a potential entry and an entity, so a query and an extract a potential entity. An LLM prompt is used to analyze the human query. That could be wrong, see my last video. And extract here a potential entity string. For our running example, who wrote the novel? Yes, whatever. The extracted entity might simply be the string, the matrix. And then, as you see, we have an embedding model and an entity vector database. System has already processed the entire knowledge graph and used the fine-tuning embedding model to create a vector representation for every single node, for every single entity. The vectors are stored here in the entity's vector database here for fast searching. And you say, hey, I know this is RAG. Yes, of course, this is the standard classical RAG. Welcome. So now it gets interesting because you see here we have something in addition. The embedding model and the domain data set. And this blue sub-diagram, or whatever you like to call it, shows you now how the embedding model was made so effective. This isn't just a generic off-the-shelf model. It was fine-tuned on a domain data set here on your specific triplets with the query, the positive chunk and the negative chunk, to make it highly specialized for the task. And in the next step, the subgraph construction. The goal is here to build multiple diverse evidence subgraphs, starting here from the real entity. We have now, as you see, 1, 2, 3 options. So the real entity that comes out here from the entity mapping is now fed into 3 different construction algorithms in parallel. First one is the one-hop relation knowledge graph. So what does it do? The algorithm simply retrieves all immediate neighbors of the matrix, film, and the edges connecting them. This provides you direct factual context. Then we have multi-hop relation knowledge graph. This algorithm goes deeper, exploring now the neighbors in a 2-hop path structure. No? You know this. You have additional reasoning chain needed to solve the query, maybe on a higher, more information needed complexity level. And then we have the importance-based relation knowledge graph. And you know this here, personal paste rank for the structural analysis methodology. And it finds nodes that are not necessarily close by, but are highly important or influential relative to the starting point. This is here Graph Analysis 101. Great. So what we have 3 distinct candidate subgraph, each representing, if you want, a different view of the relevant knowledge. Great. You might say, hey, this is exactly what we need. Multiple perspectives here on what we are searching for. Now we come here to subgraph fusion. So if you want, this is here a kind of an intelligent filtering, and now the integration, what we want to achieve, to intelligently combine the 3 candidate subgraphs into a single high quality, of course, low noise evidence. So as you see at first, we have here the reward model section. So all the subgraphs are fed into the reward model. This user's original query is also fed into the reward model. We remember, we evaluate this given here the user query. And this is where the query-based attention happens. You know this. And the reward model outputs simply, in the simplest case, a scalar, a score for each of the 3 subgraphs. Let's say we have 1 to 10. You get 1, 3, and 4, for example. And then we have the fusion knowledge graph. So the subgraph with the highest score is selected now as the backbone. So this is the most promising piece of evidence that we have. And the other 2 subgraphs with the lower scores are then processed. And then calculating the similarity query logic is, if you want, performed. And this involves comparing each individual triple from the lowest scoring graphs to the user query, and only the triple that pass here a certain similarity threshold are deemed here good enough. And we have them filtered and back, and we have now a fusion knowledge graph that includes what we think is the best solution from multiple perspectives. And then subgraph utilization, we use here the final fused subgraph to retrieve here the best possible context for the language model. It sounds simple, but it seems to be quite complex in the dependencies that you have to care for. Let's say here in the subgraph utilization, we have 3 query expansion paths. And you see those here, we have 4. Use here a general version. So you have the query and the entities, this one here, the query and the relation, this one, and the query and the triples, this here. So what they do, each of those expanded queries is used to perform now a retrieval search over the document chunk database to find here the relevant text passages that we are searching for. So if you want, this is a form of a query expansion using the structured knowledge to enrich now our search terms. Wait a second. And we come to the final processing. Everything is now aggregated. We have now a re-rank model that you know. You might say, my goodness, again, re-ranking. Yes, of course, we go to the classical structure here of RAG. Re-ranking model is applied to the collection of chunks to score them for the final relevance. Then the top chunks are selected. You have certain threshold boundaries that you defined. And then finally, the highly relevant and well-supported set of your text passages is passed here as additional information to the prompt of your LLM. And the LLM is now generating here the final output like you would expect this here from a normal RAG system. But if you look at this, especially here at the reward model, you might say, heaven's sake. This is what's necessary right now at the end of July 2025. to build here, if you want, your extended RAG system. I told you I'll give you here a prompt, and here you have, if you want a pseudocode, if you want to have it here on one glance, great. And I told you I'll give you here also here the performance data, the benchmark data, and you just have to look here at the very last line and you see, yes, of course, it's here bold. So this means it outperforms all the others. But just have a look here what we achieved, what we really achieved. Yeah? I mean, of course, if you go for LLM here with a knowledge graph without re-ranking, we have here in the simplest benchmark 8. And now we achieve here 51. But just look, LLMs in a knowledge graph plus a classical re-ranker, we already jumped to 43. And then from the other systems, we just go from 45 to 51, which seems massive. But look at different test sets and you see we go from 61.89 to 62.61 or from 41.49 to 45.96. So yeah, what would you have expected having now performed here this complex operation here where we will encounter on a, if you really want to have this on our operational level, you will encounter massive problems here from the different LLMs and potential error code. But let's say we just look at it from the theoretical level and we say this is great. Now, why I've chosen these two papers? Because they reference each other. Because now this and here, particularly the reward model of Susan, is now the solution to Gear's problem, the online synchronization step. Just think about it. This is now outside of the scope of both papers. This is just what I found, why I showed you this paper, why I did this video, because I think it's absolutely fascinating. If you read multiple papers, you see here potential cross-references that you can find solutions the authors were not even able to imagine. So the solution involves a repurposing here Susan's reward model in particular, but not as a tool for fusing here the pre-existing clean subgraphs, but if you want, as a more sophisticated semantic verification filter that you can apply directly after Gear's online synchronization step. And I think this is nice, no? Because now the reward models with graph neural network based encode and query to subgraph cross attention, it's not just evaluating here the linking triple in isolation. No, it has now the complete, if you want, absolute environment information, the context information. So it would now holistically analyze here the entire reasoning path that follows from that link. So we have more information about this. And this is here the beauty. But of course, be prepared to build this reward model and train this reward model, integrate this reward model here from two research papers might not be the simplest path forward. Okay. Yeah. Now the third paper, and you see here July 22nd, 2025, PyG. Now you might say, what is this? We know PyG, no? Yes, but this is a brand new paper. Also here, under the supervision from Jure Leskovec. And they say now, hey, what is the latest that we found in the latest version? We just want to show you what we have, and we focus here for the latest update here on 3 core aspects that have been refined and expanded here. I told you we are working with heterogeneous hyperelements, no? So the real-world graphs have diverse node and edge types, and now, or at least in PyG2, we have now heterogeneous graph data types that are now working automatically. We don't have to do it manually now for some years, and this is simply nice. But the first paper, remember, it was about scaling. And now, here with PyG, we have, if you want, the code to optimize here the scaling behavior of what we can build. So if you want, if you have paper 1 and paper 2, this PyG paper is the basement, the foundation, the operational code implementation that gives us here all the new code function and the code elements that we can implement paper 1 and paper 2 that we just looked at here in this video. Plus explainability. Isn't it nice? You know this PyTorch graph neural network, absolutely centric. Yes, this is here the classical PyG. If I have here a little talk, heterogeneous graph is now what's working here. We have graph transform architectures. Yes, you know this. illustration here of a GNN explainer in PyG. You're familiar with this. We have here multimodal, multi-table data with PyTorch frame in PyG. But of course, the most important fact is here, we can build here beautiful GraphRAG pipelines in PyG, in the latest version of PyG. Have a look at the study. If you're not really familiar with PyG, they give you a beautiful introduction into the complexity of this specific code implementation. A natural language query is used to retrieve the relevant contextual subgraphs from a larger knowledge graph, which are then encoded via a graph neural network, and the resulting node embeddings are used to enhance now the conventional LLM encoder-decoder workflow. And they have all the code instruments that we can do this in a very intelligent and a very elegant way in coding. If you want to see this here, the complete summary, I tried to give my best. Hopefully you agree with it. GraphRAG starts here with a natural language query, which is used here to retrieve here relevant contextual subgraph from a larger knowledge graph database, Neo4j for example. This subgraph is then encoded using here graph neural network, remember message parsing and everything, and the resulting node embeddings are aggregating and projected now into the LLM's embedding space. You remember the mathematical vector space that I told you that we're going to build in a, 1024 dimensional space. And PyG supports this retrieval workflow through the extension now of its feature store and graph store abstraction. Interface is fully customizable, and we can build this with elegance. G-retrieval model, yeah, compatible with Hugging Face LLM standard for today. So this is now nice because PyG as the code, as the power that the code gives us here, we can really start to build now planetary scale knowledge graphs. So we solve here, what I had in the title of this video, the problem of scaling here our GraphRAG system to millions of documents and even tens of millions of documents. There seems to be now a solution, and as you see, all companies are working on this because they also have the feeling maybe this is the way forward in AI. I want to show you 3 elements that I personally found interesting. Please read all 3 papers, come back, and then you will see, or maybe you disagree with me, please leave a comment. And if I implement now what here, the latest version of PyG 2.0, in reference here to the 2 papers that we just looked at, Susan and Gears. So what we have is an out-of-core graph processing via a decoupled storage. And this is essential. Why? You remember Gear operates here on 2 massive independent data sources. They're used here in the publication, the Find Web as a document index, and then a canonical huge knowledge graph from Wikidata. Now, of course, a traditional GNN library would require loading one or both of these into RAM, which is, for the completeness of Wikidata, almost impossible if you're not Google or Microsoft. So what is here the PyG solution? It builds an abstraction that allows us to define a graph store that is not a memory object, but now an API client. So simple. So we can create now a Wikidata graph store and a FindWeb graph store classes. And when the Gears agent needed to perform here the graph expansion, as I showed you in this video, on Wikidata, the sampler makes simply an API call to the Wikidata index. And when it needs to retrieve those features, it makes a separate call. So we have an out-of-core computation as an elegant and the single most critical innovation, enabling now here the Gears architecture. So you see, we have the code elements to implement here Gear in a very nice and efficient way. But we have I have another idea that maybe we can implement this heterogeneous message parsing here that is really here automatically done. Because you remember here, especially here for Susan and Gear, if we would do this here in the classical manual way, it is an error-prone nightmare. I mean, at least for me. So if we work now with the 2 hetero function, PyTorch automatization, simple homogeneous GNN model and a schema of the graph, and it automatically generates here the complex multi-layered heterogeneous model. so nice, all done by the code. Everything is coded for you already. It really lowers here the barrier to entry. No? Make it feasible to define and train your sophisticated graph neural network here, especially for Susan's reward model, directly on a graph like Wikidata. It reduces your cost significantly. And the third point I would like to mention here, really the last element here, is batch sampling and computation on GNN. No? I told you that here Susan's reward model needs to be trained. We have to require here creating training batches, where each item is of course here a query, a candidate subgraph, and a score tuple, and the candidate subgraph is not a single item, but now a complex data structure. And in the latest PyG2 update, we have highly optimized data and data loader objects that can now exactly do this, efficiently batch these subgraphs together. We have a more complex data structure that can handle this, and everything is simply looking great. And you know what? The core of the reward model, everything we do is fast enough to make the training of millions of such query subgraph pairs practical. So we don't only have here the hardware computer infrastructure, but software is coming up and able to do this. The classical, I would say, way to learn heterogeneous graph learning is here the official literature, official manual. But I think I would like to stop here, have a look at the paper, get familiar with everything, because in one of the next videos we will continue to build on this and maybe go the next step. If you're interested to see more of those videos, why not subscribe, and I see you in the next one.